Thanks a lot for having me here, and thanks a lot for the introduction. It's my pleasure to be here. As you may know, I was visiting scientist of CIRMMT some years ago, I think 15 years ago or a little bit less. So it's a pleasure for me to be back to Montreal and give this lecture. And I wanted to talk to you a little bit about my field of work, which is audio-based music information retrieval, trying to give you an overview of the field together with my personal career in the following topics. So I wanted to explain you about the paradigm shift that we have lived from knowledge-based systems to data-driven systems in MIR, and also trying to give you some examples of some tasks where this paradigm shift has happened. Finally, presented some applications where those technologies or those algorithms are being used, and also which are the current challenges, and mostly which is the societal impact that our technologies are having. This is a bit the outline of my talk, and I will start just from defining, for those of you who do not know what is MIR. Of course, we have people here that are experienced researcher on that, but music information retrieval somehow was born in the late 90s with the a rise of internet and techniques such as audio compression or computing, also music players or streaming services. And the goal that our community has was really to help people find music. So we have vast amount of music data, and we wanted to create technologies that will allow people to navigate through this amount of music collection. So this was the idea that the community behind has trying to create retrieval systems. And this was a combination of disciplines. We had musicologists also that knew about music, about the structures. We had also signal processing or acousticians that work with the acoustic material of music. We got people from cognitive science to work more on psychology or perception, on cognition. Of course, library sciences, because we were looking at data and libraries, and finally computers, or people more interested in computers. So we are very proud to say that the MIR is an interdisciplinary or multidisciplinary field. Audio-based MIR is based on the notion that we want to deal with the music signals, with the audio, and this has been my main focus of expertise. Although in some of these years, I have also worked with other modalities, such as video or text. My main focus has been to analyze the audio signal. This is a very traditional scheme adapted from Michael Casey's paper, where he presented the idea of audio-based music information retrieval, where we have an audio query, or we have audio files, and then we try to define a set of descriptors according to a description scheme. We try to extract them automatically, and then we try to search in a database by means of similarity metric to define a ranked list, for instance, of results that will be more recommendation, or a not ranked list. In this scheme, you see two main components of an MIR system, which are the descriptors, which are kind of features that we're going to extract, and the similarity metric, which kind of similarity criteria. So these have been the two main problems of our community, where we have been trying to improve the automatic characterization of music in terms of descriptors and the automatic comparison of music piece by means of similarity metrics. If you see in terms of descriptors, the community is focusing on what we call the semantic gap, that is the distance between what we can extract from a signal and what humans will describe from music. So this so-called semantic gap allows us to describe three different levels of descriptors. For instance, we talk about low-level descriptors, those that are very close to the signal, and they are very directly extracted from the signal. For instance, you could see frequency components or some kind of information that is really acoustics. We talk about mid-level descriptors, those that go a little bit high up in the abstraction level. For instance, they incorporate musical concepts such as rhythm or melodies or scales. And these are, for instance, key estimation or tempo description. And then we have what we call high-level descriptors, which are those that we would use to describe music. For instance, the one most researched is emotion, or for instance, style. They have been traditionally. So the community and myself also in my career, we have tried to bridge this semantic gap between low-level and high-level descriptors. In terms of similarity metrics, of course, there has been a lot of research where different similarity metrics are give the rise to with or are related to different tasks. For instance, you see here a 2D representation. If the similarity is according to a specificity, for instance, if we want to identify the same, really the same music material, we have what we call audio fingerprinting or identification. If we want to identify rather similar in terms of concept or high-level concept, we have like category-based retrieval. And then in the horizontal axis, you have granularity. If we want to identify or retrieve music at a certain point in time, you may have this task about alignment. And if you want to identify music at a document level or at a music level, you will have more like this concept of versions, for instance, or piece. So there's no such a similarity or good similarity, but depending on the application, we have been trying, or the community and also myself have been trying to define different similarity metrics. These are really the two main concepts that I have been working with, the concept of description and the concept of similarity, which are for me the three or the different eras or periods of research in the MIR, and this also reflects to my academic career. The first one is the first era, which I call audio score content description. This was reflected in a paper that we published in 2014, where we're trying to review a little bit the state of the arts in the MIR field. First, the community was trying to extract descriptors from audio content or from score content. Initially, there was a lot of symbolic data. That's what I analyzed. For instance, we want to describe the tempo, the key. In my case, I was mostly interested in pitch, melody, and tonality. And this, you look at really the content. You just look at the sound or at the score. This is the first era. It was about the 2000s. The second is what we call the music context description. We don't need to only look at the music. We need to look at information that we can find around the music. It was found out that it was much easier to identify certain characteristics by looking at text, for instance, metadata that we could find. So people, by means of metadata, started to work, for instance, with web pages and web crawling, information of microblogging or social media. For instance, you could define the similarity between artists by the similarity of their followers, or the similarity of them in a graph that is related by social media data, or images or tags that are usually created by users. So this gave birth to other community in our field, which were the text mining or the image mining people. The third era, in my case, for instance, I was working also with lyrics and also with some textual data to combine this with, for instance, for transcription. The third area, I would say, is 2010, when the community started to consider that it's not only about looking at the music, at information, or at the music context, it's also by looking at who is listening to that music. And then there was a lot of research devoted to mostly, for instance, recommendation. This was also connected to the commercial exploitation of some of our technologies. Aspects such as serendipity, novelty. For instance, if you always retrieve by similarity, you will be retrieving very, very similar kind of items. You need to incorporate concepts such as diversity, so that the recommendations or the retrieval is diverse for the listener, or concepts such as personalization that are most related to user modeling. And finally, there was a period in our community where we started to also learn that our technologies and our algorithms were very, very focusing on Western traditions, and the researchers started to experiment with other cultures, for instance, creating algorithms for, in my case, for flamenco music, or for classical music, or for Indian music. There were a lot of people doing this analysis of how the scriptures relate to musical culture and how the technologies we were developing are really coding or perpetuating some biases in the culture that they analyze. The two areas I will focus today is this one, and 2014 is the machine learning era. I will explain later, but there was adoption of AI and machine learning in many tasks, in description and in similarity. And the era we are now is the area of society and ethics. I will focus more on these two, so you see what I mean by these two. So this was a bit my introduction to the topic. I wanted now to turn a bit to this machine learning area and explain you how do I see, but first I would drink a bit of water. As some of you may know, this paradigm shift between knowledge-driven and data-driven, of course, MIR is a data-driven area because, as I said at the beginning, it's technologies to make sense of data, so it's already data-driven. But when I talk about gap, it's the fact that in the 2014, more or less, there was an increase in three main components. One is there was an increase on data or music data that was available. It was audio, it was multimodal, it was also music platforms offer a lot of access to data, for instance, to playlists, information, to social media data. There was an increase of data sets, so this generated the possibility to analyze large scale. The second component was computing. There was an increase in computing power that allowed us to train better algorithms, more complex algorithms. And the third was then the appearance of new deep learning architectures in other areas, mostly computer vision or speech processing, that our community was trying to apply to the music domain. These three components make that almost everyone in our field was taking advantage of uptaking machine learning for different MIR tasks. This is a plot by Jordi Pons in his PhD thesis that shows a little bit the evolution of papers dealing with music data processing over the years. And you see some of them at the beginning, they were living with symbolic data, so score information. Later, we incorporated machine learning from spectrograms data, and finally, we did it directly from raw audio. At the moment, most of the approaches work with raw audio or spectrograms, so very low-level features, and so that this is what we call end-to-end learning, so that there is this idea that we can learn from very low-level representation, very high-level concepts. So this semantic gap is just approach with a machine learning paradigm. That means that researchers in our community have been shifting their work. Before they were thinking about music, they were thinking about designing the features, the similarity metrics, and the algorithms, and now they're just designing most data sets, and they are also training and computing and spending a lot of computing power to train models. So there has been a drift from knowledge-driven, that is from knowledge, to data-driven. And sometimes developers might not have a control over the complex systems they are training, but they are just trying to get sense of this amount of data. So there has been a push for, and I tell this very exaggerated, but a bias towards computer science and a bias towards engineering in our field. Let me give you some examples. For instance, I will talk about three main tasks that I have been working. One is pitch content description, second is music emotion recognition, and third is version identification. First one is a musical feature, second one is a classification and very high-level feature, and the third one is a similarity metric. Pitch is one of the aspects that has been mostly researched by your community. This is an example. As you may know, pitch is related to mostly periodicity of signals, periodicity in the time domain and in the frequency domain. So knowledge-driven pitch content description were mostly based on the analysis of periodicity. For instance, one of the well-known Ying algorithm that was using autocorrelation in the time domain for predicting pitch in monophonic. And then, for instance, we defined this two-way mismatch that was trying to detect periodicity in the frequency domain, like harmonic frequencies. And then I work a bit on trying to get not only in monophonic, but also in predominant melody. So here you have a block diagram of Melodia, which is an algorithm that Justin Salomon and I proposed in 2018 that is designed for melody extraction. And you see a little bit the different blocks. From the audio file, you get signal processing, so this is acoustic processing to extract the main components, frequency components. Then you have a salience function. This salience function, to design it, you use a bit of information from perception, like from temporal continuity and pitch continuity, and also information about music, about harmonic components. And then you try to build a time pitch representation on that, which is salience function. Then you try to get the contours, then to detect voice, and all of this combines a bit knowledge that we have on acoustic signals and perception and on music. These algorithms from 2012 was published as a plugin and has been much used by the community in the sense that it works very well for predominant melody. It has some problems when you have, for instance, symphonic music where there's no such a thing as predominant, but for pop, like very predominant voice, it works well, and we have a lot of people using for different things, from education to more transcription and so on. If you look at multi-pitch, for instance, the task becomes more challenging. And the first approaches, for instance, this one of Ansi Clappery, try to do an iterative approach where you estimated the predominant melody, then you subtract it from the spectrum, and then we try to have iteratively estimation. It was an initial effort, and in my case, I worked more on chroma features that were trying to map everything or this pitch saliency into a 1 octave, and it was very effective for some tasks, from MIR tasks such as key estimation or tonality, or tonal or chord progression estimation. So at least this knowledge-driven pitch content description was really accurate and valid for many of the MR tasks. Music transcription is still very challenging, especially some material that we have worked, like symphonic music material, which is very complex. But those knowledge-driven features work quite well for certain conditions. However, we started to use machine learning. For instance, the first approach was proposed by Rachel Bittner and collaborators in 2017. It's called deep salience. This is one of the well-known approaches where you said, okay, I'm going to train CNN, I think convolutional neural networks, from a very raw representation of the signal to try to predict that. And at the beginning, the results were on pair, but there was some challenges. Multiple F0 estimation. We also work a little bit with vocal ensembles, for instance, using CNNs with Elena Cuesta. We work also, but still, in data-driven, they are good. Those systems maybe perform similarly to knowledge-driven approaches, but there is still a problem with the data. There is a limitation on the data because, of course, you don't have so much data about with a specific information. However, now we can generate synthetic data. There was a paper that I cite here from 2022 by Weiss and Peters, where they evaluated different architectures. They saw that there is still improvements, but those systems do not generalize well to unseen data. So there is still the need to create more data sets and more standardized ways to evaluate music transcription system. However, we can say that knowledge-driven approaches have been somehow replaced by data-driven approaches. Most of the papers that we see are now based on this approximation, and then the goal is, of course, to get more data so that my systems can be improved. Let me go to the second task that I wanted to mention, is the music and motion recognition. This is a screenshot of a system by Cyril Laurier. It was his PhD thesis at the MTT. He combined audio with lyrics. And music and emotion has been one of the most challenging tasks. Also from the point of view of an outsider, it's like, okay, are you trying to predict emotion? Emotion is a human, so much grounded in culture, in human, that it seems difficult to predict or to predict computationally. However, it has been one of the most research tasks in the MIR field because it has many applications, from music recommendation to therapy or marketing. For instance, there's a huge use of this kind of material. So there has been a lot of investment on this task. This is the standard MIR block diagram for a classification task, which of course is traditionally data-driven. This is by default a machine learning. However, at the beginning, we used some kind of knowledge. For instance, there was first, they need to define a taxonomy for music. We have categorical taxonomies, and we also have a dimensional taxonomy, like balance and arousal. There was some knowledge, for instance, on the annotation of data. Annotation of data is challenging because it's a subjective characteristic. It also personally grounded and culturally grounded, so there's still research on this. And there was knowledge also in which kind of features. There's a lot of huge literature in music cognition analyzing the link between music and emotion. So there has been some scientific knowledge about, for instance, the kind of features that are relevant and the kind of features we need to consider. For instance, tempo, articulation, tonality, dynamics, timbre, and also contextual information. For instance, lyrics is also much grounded. So these were the first approaches. You have feature extraction, then you have a training of a model up, and then you have a classification in, for instance, in categories, or a regression, for instance, logistic regression in access. And then you have this difference between training and testing, and so on. Of course, this can be applied to other tasks. I have worked, for instance, in style classification. We did only based on the singing, on the vibrato rate. We did a system to classify different singing styles. For instance, it was flamenco, jazz, opera, pop, and vocal jazz, and instrumental versus vocal. And also we did a project on classification of preferences or characterization of musical preference, which was called musical avatar. What's the main drift or the main shift in this task? Of course, this whole process of crafting your classifier has been now much converted into an end-to-end process. For instance, we have time frequency representation of the signal, and then we can have different architectures. I put this by directional short-term memory, which has been used a lot, recurrent neural networks, convolutional, and all of these are really trained on raw information. So then there's a lot of knowledge that we have about music, about the signal, that is not really incorporated. It's maybe incorporated indirectly into the architectures or into the data and the data annotation process. We made a study on, I think recently, it was in 2021, where we tried to see which are the challenges on music emotion recognition. And we saw that, of course, This task is quite subjective. There is a personal dependency. There is a cultural dependency. So it's still challenging. I mean, some of these systems may appear to be right, but they may not understand really what is emotion or what is music. I will get back to that later. There is also a challenge on the data. They're data sets, but they are always of a very particular, the data sets that are curated are small, and then there are large data sets, for instance, those coming from playlists that are not validated. So it's difficult, I think, to find large data sets. There is a lot of research on personalization and some techniques that, for instance, we use to try to get personalized modeling, but of course you then need personalized data. And this is also hard to find. And another challenge is to deal with temporal changes and temporal variations. So in this aspect, this has advanced, and maybe this drift in machine learning has much advanced the field, but there, of course, is this challenge to address. Finally, the last task that I wanted to talk is about version identification. Version identification is one of the most researched tasks in similarity because it also has a commercial need that is to link to copyright protection, and also there was a need to find versions of the same song in an automatic way. The detection of a song and dispersions is kind of a musicological problem. Which are the characteristics that varies in a version? Traditionally, from the pop domain, you have changes in key, changes in tempo, changes in structure, and these are the most basic modifications. So these are the overall block diagram for a version identification system. You have also a set of features, structure again. Then we have to implement 3 blocks for ensuring invariance to transpositions, invariance to tempo, invariance to structure. And then there was some similarity estimation. And then you need to find a threshold. What is a version, or what is a cover, what is not. So these are more or less the problems where we have been working, or the community has been working. In my case, I published my first paper in Izmir in Victoria on this, and also it was part of my PhD thesis, and then we were trying to use chroma features for the comparison. It was pitch content information is a feature that is mostly used for version ID. Transposition is managed by normalizing pitch according to maybe instead of absolute, we get relative values according to key. Tempo invariance was managed by having features that are bit synchronous, and structure changes are managed by comparing locally pitch content information instead of globally, so you can incorporate some variations in the structure. And finally, similarity, if you consider the 3 next steps, is quite basic and was based on correlation. How has this is more the knowledge-driven version identification. In the data-driven approach, you treat this task as a binary classification task. Either 2 songs are version or 2 songs are not version. And then you try to train the model with data sets where you have songs, and then you have versions of the same song, and then you show them these examples, and then this is the idea that is behind. Of course, all these aspects of transposition invariance are somehow translated to deep learning concepts. For instance, you can have a convolutional layer that will ensure transposition that will try to shift your pitch representation differently to account for this transposition. You can also have some latent representation that are tempo invariance, and all of this is done mostly with a very low level feature. Mostly chromogram would be, or directly as a frequency representations. There has been many challenges in this field. For instance, there has been a lot of work on accuracy versus scalability, because of course, if you want to be very accurate, you need to compare or take a lot of effort in comparing two songs, but this is not very, very fast. So usually, traditional approaches were very good at performance, but very bad if you want to scale up to real-world scenario. It's impossible. So other approaches that were maybe simplifying the embedding or the features were less performant, but also were fast. So a lot of this work, for instance, we were with Furkan Yesiler and John Serra on trying to study this accuracy and scalability, because mostly this is a task to be implemented large scale in real world scenario by actors. And I wanted to mention that these kind of algorithms have other applications beyond that. For instance, we are now using it for with Rosa Batlier in her PhD thesis for the analysis of replication. It's how the generative AI model replicates its training data. So if you compare the outcomes of a generative AI model with the training data and see if they are similar, you can say that they are somehow replicating. So we are using that also to evaluate models. And there, I think this idea of similarity or musical similarity is very interesting for other applications. Of course, this method works well for versions that are very similar, but the concept of version and the concept of reinterpretation is also complex musically. So there's not much we can solve with a trained model, because it's difficult to. There are different kind of versions in the same concept. So this is a bit. I hope I managed to explain or to transfer which have been, in my view, the paradigm shift from our field to devote time or to trying to, I remember there was some people saying, okay, it took a PhD thesis to design one feature, and now we can design it automatically, okay? So, of course, it takes now one PhD thesis to train a model. Of course, it takes more. And so there are different ways and different skills that are now needed, and different tasks where we are devoting our time. And I wanted to, in any case, to show you now some applications. Of course, the MIR field is being very active. I show here some statistics, which unfortunately are not maintained until now, but you see a little bit the trend of the field. There's a lot of industrial impact of our field. There are many companies that are making business on MIR and trying to design products, for instance, from education to music streaming platforms, and it has become a very, very applied field. But I wanted to show you maybe some examples of applications and projects I have been working, which go a little bit beyond this kind of applications. This is a project where I was working for a while. It's called Cante Flamenco Tech. And I think also when I was here in CIRMMT with Caterina Gustavino, we were working on flamenco rhythm. And these technologies are very useful for oral music material where there are no score information, and we can really characterize, for instance, in flamenco, there's a lot of ornamentation in the voice that are not notated and are not really characterized. So it was, I worked in a project where together with a flamenco singer, we create a massive open course on teaching or learning how to sing flamenco with visualization of pitch and description of melodies, because it's difficult sometimes to hear it, but if you see it, it can allow much. I didn't put the video because it's Spanish, the course, but we developed also data sets for flamenco singing. We created a data set of tonas, which is singing voice, and also another data set of flamenco styles because there is not much research on this kind of oral tradition from the academic setting. So this is one project that I worked. The second project that I devoted a lot of time was Phoenix. Phoenix is called, I don't know the acronym, I don't remember anymore, but the idea was to use MIR to create new experience of music concerts and to provide added value to a music concert before, during, and after the concert. We were dealing with very, very complex music material, mostly symphonic music material, and Trompara was an European project that was getting together different partners, different people. For instance, we have TU Delft from technology. We have also Concertgebouw Orchestra in Amsterdam that was a big orchestra. And we tried to build applications, for instance, that could help you, for instance, personalize the music program according to your knowledge of the music, provide information during the concert on the structure. One of the most demanded facility was to know where we are in the piece or in long pieces, and then maybe after the concert, to be able to listen to some of the aspects or to compare. So this was a product that, or a explorative work that we did. And I wanted just to play a video of one concert that we did with real-time MIR, which was also challenging at that time because it's not the same to do things in offline that doing in real time. We discovered that the symphonic music is already a big data kind of asset because, for instance, we recorded the Ninth Symphony of Beethoven with an orchestra that we have a data set, which is the ninth with all instruments, and we did the score alignment, and it was a major effort. Only the data we had with one symphony was amazing to experience that. And of course, MIR didn't work with such complex material, basically. I put you a video of this concert where we tried to do some visualization in real time. We worked with the Youth Orchestra in Seville. Let me play it. This was in 2015, and we had some trouble with the score following. So at the end, I was like, directing the score, following from the back. But this allows us, for instance, to do some comparison of different conductors, and we did recording with different conductors, and yeah. This was, now I see it, and it seems like an old video from the resolution. This other project where we work was with music communities. We work with communities in 5 different communities. One was choir singers, and during the pandemic, it was a project Trompa that was in the pandemic where choirs couldn't rehearse. It was very difficult for them to rehearse. And we came up with this Cantamos, which is an app where to aim to support singers in the choir practice. So we use singing voice synthesis because in MIR there is also generation, as well as you can describe, you can generate, and we use it to develop this tool for people to sing along. You have here and then to rehearse. And the challenge here was to work on multilingual singing voice synthesis. We worked in Latin, Spanish, and English, and also to have this interaction with people during this period to make them feel also as part of the choir. I will play a video of this as well.
Sword and shield, down by the riverside, down by the riverside, down by the riverside. Gonna lay down my sword and shield, down by the riverside. Gonna study war no more, study war no more. I ain't gonna study war more. Ain't gonna study war. I ain't gonna study war no more, no more. I ain't gonna study war. Ain't gonna study war no more. Ain't gonna study war no more. I'm gonna lay down my sword and shield down by the riverside. Down by the riverside.
Yeah, so this project was very interesting. It was very nice to work also with Unison Choir, trying to characterize a bit pitch content from that. We also created many data sets. One is the choir set. And we also had the experience to work with virtual choirs. And especially in this period, it was a coincidence that we were working on that topic, and we managed to do the project. And finally, just the last project, maybe we saw a video that we work. This was the one that get the Crossroad Award. We got a recommendation system for Alzheimer patients in Barcelona. This, we discovered the big bias of recommender system toward young people, because those systems didn't work at all with people of that age. I mean, the musical repertoire was not there. It was the people wanted this song not. It was very difficult to find the right cover, so we had many challenges, and we use this. It's called Live Soundtrack, and we use it. This was a very nice project. And finally, of course, I contributed to Essentia, which is a library where we integrated all the scripters in the MTG. So I was integrated, or I was contributing with some of the descriptors that I have been developing. So I think I have a few minutes left that I wanted to discuss about the challenges that I see in the field, and also what it takes my time now, which is to analyze what is the impact, because after many years developing technologies, I just realized the impact that those algorithms may have on people, and also how important it is to make sure that this impact is positive, and that we are creating technologies to help users find music, not to to help to do other stuff. No, so that this idea of our community helping people, it was very naive. So I'm working a lot on this at the moment. The challenges I see in the field is data. There's a lot of effort that is built into building data set. I've published many data sets. Most of my most cited papers are data set papers. For instance, in Cover ID, we did a data set. And we have also this problem of copyright material, but it's difficult to share music data, but there's also there's a need to preserve also the copyright for this data. So because those models that we train on copyright material will then be used for some tasks, so we need to reflect on that as well. This is a big issue, and there is also a big issue in annotation. We have data, but the annotations are not usually good quality. There is a bunch of literature, a bunch of knowledge on cognitive science that our community is underexploiting for having good annotations. There's aspects such as inter-rater agreement or also subjectivity and cultural context that needs to be done for annotation. So this is a big issue where we need to devote a lot of effort. There is a bias to weird participants, like Western, educated, industrialized, rich, and democratic. So there is also a lot of bias on our data. Second challenge I see are MIR really learning about music. Bob Stern worked in this concept about clever hands effect. I mean, those systems are as one colleague was mentioning about LLMs, they are trained to seem right, not to be right. No, so those systems are trained to seem to know about emotion, not to really understand emotion. So, which are the knowledge we are gaining as humans on these kind of systems? Is if the knowledge that we have is not enriched. So this is also I put here the need for more musicological analysis on those systems and what they produce and what are the implications they have. Another challenge is this idea of we are shifting from human knowledge to machine knowledge. And I like this example that say, okay, AI, when you say AI, this word is tedious, maybe a computer can do it for me. Or when we say machine learning, oh, it's really difficult to program, maybe I can, if the machine has the right structure and good examples, it will learn by itself. And the third one is deep learning. I don't know how to make this computer understand. Maybe it will create its own structure. So we are somehow losing our knowledge, or we are somehow not in control anymore of the algorithms. There's a lot of course, engineering side. But I think we need more effort into evaluation, or rather than to only deployment. But also we spend a lot of effort in building, but not in evaluating and understanding limitations and challenging. And this is also a challenge that we see, because there is a difference between human knowledge and machine knowledge. I have here a paper that say, okay, humans have individual opinions, machine learning have averages opinion, humans have a priori knowledge, but machines need to learn from scratch. Humans can learn models and use it for other things. So there's a bunch of differences, and we are somehow trying to replace human knowledge, but we should more aiming at complementing human knowledge. And this is also an underexploited area in our field, which is human-computer interaction and how we can combine human and machine intelligence. Of course, MIR can just measure very, very fast vibrato that we cannot. But there are some concepts such as emotion that maybe it's not make sense that a machine can say what is happy or what is sad. I don't know, but this is something we should be checking. And finally, just to finalize a bit about societal impact, of course, there's researchers that are involved in MIR, but there are also listeners. They're also developers, and they're also music industry. Listeners are not much represented in our community. There's industry, there's developers, but there's not about the people who are impacted by those algorithms. And this is a bit what I have been working on. For instance, I've been working a lot, let me show you, on this concept of trustworthy AI, which is that AI systems should be trustworthy. It should be, this is a concept defined by the European Commission high-level expert group. They say that a system to be trustworthy has to comply with 7 requirements. One is accuracy. One is privacy, there's fairness, there's transparency, there is accountability, and there is societal and environmental well-being. So all these are the neglected dimensions when we evaluate an MIR system. We evaluate that they perform well, but we don't evaluate if they are fair or if they are preserving personal data. For instance, in terms of fairness, we have seen that MIR may reinforce societal biases. This is a master's student that was supervised with Lorenzo and Porcaro, Carlos Casillo, and myself, that we show that in certain recommender systems, there might be some algorithms that might perpetuate gender bias in recommendation, for instance, collaborative filtering versus content-based filtering. So we see that maybe the approach that we select can have effects on biases, and this can have really effect on people that are being recommended or artists that are being recommended. But when we design an algorithm, we are somehow isolated from its social context, and we don't really know about the effect. But I think there is something we need to learn, that the MIR system are socio-technical system. Another problem is that MIR needs to consider cultural diversity. We have a project as well. It's called Diversity by Design in Recommender System, so that recommender system can be diverse and can also adhere to different musical cultures. And also, MIR should be more transparent. And this is a project we have on transparency, where we're trying to see how models are trained on data from artists or from creators, and which are the implications it may have for those creators when AI is generating music is used to cut costs, for instance. And there's more need for transparency. These are papers on transparency. They are increasing in numbers, so I think there will be a field where we need to work more. And final is about MIR and regulation. I'm now working at the European Commission, so of course I'm very close to regulation, but there's some regulation linked to copyright, for instance, that is being discussed in this field, if we need to change or adapt to the new developments in our field. So now MIR is there, it has practical application, and it's having societal impact. And we need to study a little bit more. So conclusions, we need to find a balance between the opportunities that our technologies bring to society, but also the risks that might bring as well. And finding the balance needs, again, to incorporate more and more disciplines. So we need to get back to musicology, to cognitive science, to library science, to cognition and acoustics, to try to make systems maybe that are less costly, that consume less energy, that are more transparent. And this is a bit how I see the field and the research to come. Thank you very much for your time and for your attention.